So I welcome all of you to the 25th session of Webcast Wednesday, and today we're going to discuss the timing options in LabVIEW. My name is Jagrati and I'm going to take you through this presentation. So timing is one very crucial aspect of your applications, and most often it's quite neglected, and this can lead to dire consequences at the end of your application. So today I want to take this chance to explain some of the timing operations that we have in LabVIEW and the ways you can integrate this in your application. So it is very important for you to understand all the operations. So let's look at the need for a timing. Timing, as we all know, is quite an essential element for all design, test, and control applications and should be a very key consideration in any system. So now before I go on to explain what timing is, I would like to take this chance to quickly take a poll from all of you to understand how comfortable all of you are with timing in LabVIEW. So just take a couple of seconds and answer this question. Yeah. So please let me know on how comfortable you are with all these functions in LabVIEW. Have you used these in your applications? Do you know why it is used? Okay, so I see a lot of you have said you don't know what these functions are. Some of you have claimed that you know some of these, probably about the weight functions, you're comfortable with them. Let me take this chance to clearly distinguish what each of these are and when you would use each of these with appropriate demonstrations. Okay, now let's try to understand why you need timing. Of course, we know that when you're using a loop, we need timing to control the rate at which the loop is executing. Because if we don't introduce timing, the loop will run at the fastest possible speed that your system can accommodate. Now, this seems like a really good option, but it has a downside to it as well. If you allow one process to take the entire resources of your processor, then no other process can work on your processor. They'll all get queued up. And if not enough time is given, it can eventually cause a crash of your system. So if you have applications that are running for a couple of days, weeks, maybe even months, and if you've not accommodated for timing appropriately, then that can cause a system crash eventually. So let's try and understand how to avoid all of that, how to use timing in the best possible way. So this is the timing palette. I'm sure most of you have seen this, and you've probably used one or two of these quite frequently. So we have the tick count, wait, and wait until next millisecond. These are the three most commonly used and the three most important functions when it comes to timing. We have some other operations that help you manipulate the date time function as well of your system time. That we will come to a little later. I'll in brief explain what all of those mean as well. In addition to tick count, wait, and wait until, I'm also going to take another function called elapsed time. It's a very interesting feature, but very, very seldom used. Okay, so the first one saying tick count. Now tick count is a very simple operation, and all it does is it gives the output of the current system time in milliseconds from the time you have booted your system. Now standalone, it does not make too much sense to know what is the current millisecond timer of your system clock. But when used in conjunction with another tick count, you can actually try and understand how much time specific portions of your code take to execute. So you can use two tick counts and use it with a subtract operation, and the output of that will give you the time a particular application takes. So we will come to that in the demonstration that I'll be showing you. The next operation we have is wait function. I'm sure most of you have used this quite frequently in your application. All you have to do is you have to give an input to this function in terms of milliseconds, and this operation just waits. It just makes the entire code wait for that much amount of time. So it runs in parallel with the rest of your code. So if you have a code inside your while loop and in conjunction you have placed this wait function, then both of them will run parallel, and the number that you give to wait should be a little more than the amount of time your code will take to execute. So let's quickly take an example of how this can work. So suppose I have wired a 10 millisecond value to my wait function. And if my current system millisecond timer is 112 milliseconds, let's just take that for an example. Now for my first iteration, this function will cause my loop to wait 112, that is the current system time, plus 10 milliseconds, because that's the input that I've given it. And that will cause it to wait for 121 milliseconds for the first iteration. Second iteration, it will simply add another 10 to the same 121 and make it 131, and so on. So it does not really take the system time into consideration. It does not recognize the system time. It just, whatever it is, it just adds a 10, irrespective of what the timer is. Now, if you have understood this particular function, the next function of wait until, you can see the contrast in what the wait until next millisecond multiple function really is. So it looks similar to the previous function. You just have to give it a value that it has to wait. So say I give it again a 10. Now how is it different from the previous function? Let's take an example to explain it. Same example. Suppose I wire a 10 milliseconds to my wait operation and my current system millisecond timer is 112 milliseconds. For an example, let's just take 112 milliseconds. Now, how far is 112 from the closest multiple of 10? Closest multiple of 10 from 112 is 120. So this particular function of wait until next millisecond, wait until next multiple, will very intelligently look at what your current system time is. And based on what the current system time is, it will add an appropriate amount of time for the first iteration to make the system time a multiple of the value that you have mentioned. So if my current system time is 112 milliseconds, it will simply wait for 8 milliseconds during the first iteration, thereby making it a 120 milliseconds. Once it has made it 120 milliseconds, now it has synchronized the time with my system time. So now on, it will simply add a 10 each time, so you know for sure that this particular loop is executing at multiples of 10 with respect to my system time. So this is a very important function when it comes to synchronizing, because if I put different multiples, say I give different prime numbers in my millisecond multiple, if I do that, I know that multiple loops will always run at different instances of my system clock. I know they will never happen at the same time. They will always happen at different system time. They will always happen at different multiples. So it is as simple as that. So you can use this function if you're looking for extreme amount of synchronization, in addition to giving your processor time to sleep, just like every other function. Just like the wait and the wait until, both of them give equal amount of time for your processor to sleep, but this in addition helps in synchronizing. So next time you see this function, keep in mind why it is used and how it is different from the other function. I have been asked if I can show a demo. Very quickly I'll show you a demo on how these two are different, so you can actually see the values varying for the first iteration. So let me just come to that in a while. Before that, there's another very interesting function, like I said, elapsed time express VI. Now I'm not sure how many of you have used it, but it is a very useful function. Now this can essentially be used as a trigger within your application. How as a trigger? Say I run my code, and after I run my code, at some point, say 10 seconds after the code runs, I want another portion of the code to run. Only after 10 seconds I want it to start running. And that is sort of a trigger, right? So you can use this operation of elapsed time to act as that trigger. So what this does, it does not pause any execution. It simply runs alongside, keeping a track of time. So this is an express VI. So if you're familiar with express VIs, you know that if you double click this, a configuration box opens up. So the configuration box for this simply asks for the time that you want this particular function to give the trigger signal. So if say I give 10 seconds and I run my code. Now this particular function is internally counting until 10 seconds. The moment 10 seconds has been reached, this time has elapsed option that you see right here will give a true. Until then it will keep giving a false. So you can use this true value to trigger a portion of your code. You can have anything. Say something after this, you can have a case structure. So you can put that portion of the code that you want to execute after 10 seconds inside a case structure and give the output of this time has elapsed to the input of that case structure. So that way you're causing a very, very convenient way to have an internal trigger in your software without any hardware interference. So this is an application of Elapsed Time Express VI. I'll try and show you a small demonstration for this as well. Okay, so let's so now I will show you the three functions that we learned about: the tick count, the wait, and the wait until. First, let me show you three of these. So the best way to demonstrate is, of course, with a while loop. So let me draw a while loop. And inside the while loop, I need to put some kind of code, and since this is a demonstration, let me just simply create a chart with random numbers. So I'll simply place a chart here and I'll wire this here. Okay, and I'll make a stop for this. So now this is my application. If I run this, by default, this will run at the fastest rate that my system is able to accommodate, because I'm not yet given any sort of timing. But the wise thing to do in any application like this is to give it timing, otherwise it will continuously utilize resources of your system. Okay, so now let me first work with this is the timing palette. I'll simply pin it here. Now let me demonstrate the wait function first. So I'm placing a wait here. Let me give it a time of, so this takes an input in terms of milliseconds. So if I want in terms of seconds, just multiply by 1000. Let me take 1000 because I want you to see it. If it's 100, yeah, if it's in milliseconds, it'll be really fast. So I'll just keep it 1000. Now even if I run it, I will see an update once every 1 second, very slowly. But how do I verify this as actually happening in 1 second? Now that is when I will bring in the concept of the tick count. So this is my palette. Now I will use a tick count. So I told you what the tick count does is it simply gives the output of the current system millisecond value. Okay. So standalone, it's not going to make too much of value to me in this particular application. But what I'm going to do now is I'm going to place two tick counts. Now, as we all know how while loop works, it takes an input only at the start of the execution. So this value, that is the current system time before the loop starts executing, will be stored here. Then on, this value will not be taken. Only the first value will be taken. This will continue giving the current system time and it will continue taking it. So I can utilize this property of the while loop. And now what I'll do is I'll just place a subtract. So if I subtract the current tick count from the time this application started and I give an indicator within the loop itself, I will see a real-time update of the amount of time every iteration takes. So now when I run it, you will see that this particular value is updating in multiple of thousands. You're able to see it because I've actually put an indicator, and you can see it exactly in multiple of 1000. That is 1 second. It's executing once every 1 second. You can also make it slower. 100 milliseconds is a good estimate. So you see it's increasing in increments of 100 milliseconds. So this is, I ran it for about 5 seconds, you can say. Now I want to see how this function is different from my wait until. So I'll simply copy the same code down and let me close this. I'll simply copy the same code down. I'll wire this right here. Okay. Now I'll just replace this with the wait until. Same value. Now I'll make it a little bigger so that you can see it. Okay. Now just observe this. This is the difference of iterations in the second loop. This is of the first loop, which is using wait. This is using wait until. Now, if you observe the second value, when I run it, you see it is incrementing in multiples of 1000. It's not incrementing in multiples of 1000. It's 1000 plus some value. Why is that? If you again observe this, you will see. Okay. Another thing that I have to do here, because I have two stops, I'll just delete this stop. and I will create a local indicator for this. A local variable, sorry. So that I have one common stop for both the loops. Now this will show an error because it is a latch. Latch does not support variables. So I'll just change it to switch. But switch, if you change it into a switch, you should always initialize it outside your loop. So I'll wire a false here. Okay. Now when I run it, just observe this value. This value you will see does not wait for 1000 for the first iteration. It always waits for a value lesser than 1000 because it is trying to synchronize with your system clock. See, 360. That means at 360 it has reached the multiple of 2000 or 1000. If you want to again observe this better, you can give an indicator to each of these values. It's the other way around. So you can give an indicator to each of these values. This indicator is nothing but the current system time. It will be in thousands, the value, but you can see if it is a multiple of 1000 or not. In this case, you will see that the value is not a multiple of 1000. So when I run this, so first time you see, this is simply incrementing blindly 1 second. It's just simply waiting for 1 second. Thereby the millisecond timer is incrementing by 1 second. But this has synchronized it and now it is only running at multiple of 1000. So you see the stark difference between these two operations. Okay, so this is a small demo to show you the difference between a wait and a wait until. Now, like I said, I'll just try and quickly show you what the difference, how the elapsed time works as well. So for that, let me open a new code. Okay. Where is the elapsed time? You can locate it right here. This is the elapsed time function. Let me place it here. The moment you place it here, there's a configuration dialog box asking you how much time to wait. Let me just give it a 3 seconds. Now it doesn't make sense to use it without a loop, so let me place a loop. And again for demonstration, I'm going to show you the same example, the random number and the chart. So I think previously in one particular session you would have seen why we can use chart inside a loop and graph goes outside a loop. Because graph takes inputs in terms of arrays and chart can take instantaneous values, single values. So now what I want this elapsed time to do is simply stop the code the moment it reaches 3 seconds. Now that's a small logic you can use elapsed time for. So as you know, this will give a true at the end of 3 seconds. So I'm going to wire this time as elapsed to the stop terminal. So what this will do is if I run it, it will simply run continuously at the fastest speed possible for 3 seconds and it will stop automatically. Why fastest time? Because I'm not giving it a timing inside. Like I said, elapsed time does not cause your code to stop. It just runs along with it, along with the rest of your code. It does not give time for your processor to sleep. Now to show you the difference between this and the other function, let me just use a wait again. Okay. Now I want this and this function to run for the same amount of time. And notice I've placed a for loop here. How can I cause it to run for the same amount of time if I give this 100? I just want to show you a demo, so I just wanted to run it at the same amount of time. If I give this as 100, I should give this as 30, right? If I want to make it 3 seconds. Because 30 into 100 will make it 3 seconds. So just observe how these two different charts are updating. Now when I run this, you see this is running at the fastest possible speed, whereas this is updating. That is the DT is changing. DT is changing because I have given it right here. But both of them stop at 3 seconds because I've just used that little mathematics there. So you can use this particular function to also alter the DT of your graphs. Okay, let's just go back. Slideshow. Yeah. So this is the next couple of functions available in the timing palette. We kind of discussed about the tick count, wait until, and the elapsed time. Now let's talk a little bit about the other functions that are available. So we have get date time. So this gives you two separate strings for your date and your time. We have get date time in seconds. Date time 2 seconds and seconds to date time. There is a timestamp and there is a format date. Let's just quickly see this as well. So this is my palette, timing palette, and I have these other functions. These are not quite often used. We get a lot of customers asking us on how to work and manipulate the current system time. And these functions are very interesting that way. You should try and exploit these as much as possible. So this function simply gives you the current date and time in two separate strings, because a lot of times you want to manipulate date and time in terms of strings. And date, time, data type in itself, you cannot manipulate it directly. So this directly does that for you. So all you have to do is create an indicator for this. And create an indicator for this. And when you run this, you will get today's date and my current system time in two separate strings. You also have an option to get the entire date together and also the seconds if you want seconds. So as you know, Windows system goes until millisecond count, and that is what you will get in the last 3 digits here. So when I run this, you will get in terms of seconds as well, and the date and time together. But the data type, of course, is the timestamp, is the time data type. Another operation available is the date time to seconds. So what this does is it accepts different parameters of the date time value and creates a timestamp of it. When I say parameters, it expects everything in terms of fractional seconds, hours, minutes, days, months, years. So you can give each of those individually and it will create a timestamp out for you. So if I just simply create a constant here, you will see it's a cluster of all these values. This can be used many times when a particular portion of your code is, say, generating just the hours, a particular portion of the code is generating the minutes, something is generating, say, the day or something of that sort. You can individually club all these together and give it to this particular function. So if you do a Control H here, you will see what are these different functions. So you have to give the second, minute, hour, day, month, year, day of week, day of year. So once you give these values, the output of this will be a timestamp of this sort with all the values together. It will automatically calculate all that and give it to you. So this function does exactly the opposite. So this function takes the timestamp. So since this particular function that I had here gives me the timestamp, I'll just give the output of this. And when I create an indicator for this, you will see that it gives me, it just basically splits up the entire timestamp and it gives all the functions separately. So when you run this, it gives all this value, current value separately. It just splits it all up so you can use it individually. You don't have to manually do that. And this, and if you give the output of this function to the input of this function, it will simply put everything back together and give you the current date time. It's just giving the current date time. Of course, this is not something you would do as an application, so I'm just doing because it's more convenient to show as a demo. But when you're actually working at your end, you will use each of these individually and create this automatically. This is one application. So to show you an application, it's already made, how this can be used. So here all we're doing is we're just simply creating a very simple waveform, very simple waveform with 20 data points and random numbers. This is a build waveform operation. This you will find, so this operation you will find in the analog waveform option. You find it right here, right? You find build and you get waveform. So here you're programmatically building this particular waveform. Why? Because you want the timestamp to be on the x-axis, and you also want to manipulate with the dt value. So you can use this particular function. So here I'm just simply giving the amplitude, which is nothing but the random numbers which have been generated. I'm giving the dt here and I'm giving the t0 as the current system time. And this, when I build it up, This is the waveform I see. There are a couple of other functions, very interesting functions they have used here to get the final time, that is when does this stop executing. Now you can manually calculate it. The final time here, since this is a for loop, I know what the final time here will be. It will simply be 20 minus 1, that is 19 into 0.20. So that will be the final time that this loop has executed. Sorry, that will be the duration, I'm sorry. Final time will be the system time. That is adding this particular value to the current system time. This will give you duration. So these are all different functions that are available again in the same palette right here. So here I'm getting the final time value. You can get the amount of time your waveform was generated for. You can also get the number of samples. So this is a small example of how you can incorporate your date time function inside of LabVIEW. Okay, so that was about today's webcast. Coming to the question of this week. So we have two different questions depending on your level of comfort with LabVIEW. For people who are just starting off, please try the first question, which is I want you to create a VI that generates random numbers between 1 and 1000. And as a user, you have to give a particular value between 1 and 1000. And you to see the amount of time it takes to match that value, because random numbers are continuously varying from 1 to 1000. How much time it takes to match that number that you give. And I'm going to display that, and as well as the iteration count. So for those of you who are comfortable with LabVIEW, I want you to generate a sine wave. And now this second question uses a little bit of property notes, so if you're comfortable with that, please go ahead with this. So I want you to generate a sine wave with DTS 0.1 seconds, and every time the sine wave, that is the amplitude, exceeds a particular threshold given by the user, I want you to change the portion of the graph indicating a warning, say either red or blue, something apart from what it already is. So you can try either of these two questions just to understand the concepts that we've learned today. In addition, if you have any doubts, please post a question in the same place asking us, and we will explain it to you again. So as you know, we have an extended learning on the LabVIEW enabled community. So end of every webcast, we put up contests, there we put up questions. You can also view the previous episodes. So if you missed this episode or any previous episode, you can always watch it again on the community, LabVIEW enabled. You can get all your queries resolved. It's not just you answering the questions. If you have any queries, please ask us. Also interact with all the other peers and industry experts. In addition to all of this, the person who wins these contests, so we judge and we get one winner from all of this, will get a 50% discount in CLAD. Continue attending 20 such sessions of webcast and you'll get a free attempt at CLAD. The question has been posted live on your chat window. You can click on that link and directly land up on the question page and start answering your question. How you can interact with us, how you can get in touch with us, go to www.labviewenable.in, click on the Webcast Wednesday graphic on the top left, and as you click on that, that will take you to the Webcast Wednesday page on the community. So see you all again next week. If you have any questions, please post as of now.